Let's continue to explore digital signals and logic. In this lesson, the core concept will be evaluating and taking a look at different logic gates. Digital logic circuits form the basis of computational devices, from your Arduino microcontroller to your cell phone, all the way up to your laptop computer, constantly performing arithmetic operations using logic gates. Here's an example of a digital logic circuit. These circuits have inputs and outputs. Here we have three inputs in this circuit, A, B, and C. C is a carry, in this case carrying in from a previous circuit or operation. And here we have two outputs, S for sum and C for carry out. Logic circuits and the logic gates contained within are going to be described by truth tables. Truth tables are an exhaustive listing of all the possible inputs. Remember, these are binary inputs, zeros and ones, and the resulting output. So if we go back to the preceding logic circuit here, we see we have three inputs, A, B, and C, and two outputs, S and C. So we can create then a table that will describe the performance of this particular logic circuit. On the left, we'll have our three inputs, A, B, and C in, and on the right, we'll have our two outputs, S and C out. Now, this particular circuit is performing binary arithmetic. So if we look at our three inputs, we have 8 possible combinations. Remember, 2 to the 3 or 8 possible combinations. So an exhaustive listing of all the possible inputs will look something like this: 0, 0, 0, 0, 0, 1, all the way down to 1, 1, 1. And since this is a summing circuit, we can now define our outputs. So in the case of my inputs is 0, 0, 0, 0 plus 0 plus 0 is 0, and there's nothing to carry. So I'll have a 0 for S and a 0 for C out. 0 plus 1 will give me a sum of 1 with nothing carried. Same thing for the next row. And then 0 plus 1 is 2. So I'll have a 0 for the sum, and I'll be carrying 1 on carry out. And I'll continue to fill in my truth table here until I've explored all of the outputs resulting from my 2 to the 3 possible inputs. There are a number of logic gates that are combined to perform the logic function of these digital circuits. Here is a summary of these gates. We'll now dive into some of these logic gates, and we'll come back to a summary at the end of this lesson. So let's take a look at a few of these logic gates. And let's begin with the NOT logic gate. This is more commonly referred to as an inverter. And if you were to draw the gate, the symbol will be a triangle with a small circle indicating the NOT functionality. Now there's a single input, single output to this gate. The input will be labeled as A. Typically for logic gates, when we talk about inputs, we start at the beginning of the alphabet, and outputs we start at the end of the alphabet. So our output then will be labeled Z here. Now remember, the truth table is an exhaustive listing of the inputs and outputs. Well, in this case, a digital signal A can either be 0 or 1, right? Low or high. So our inputs, A, will be 0 and 1, and it's a NOT logic gate. It's inverting the input, so the outputs will be 1 and 0. So anytime A is low, Z will be high. Anytime A is high, Z will be low. So the output, Z, is going to be 1 if the input is 0, and vice versa. Now in terms of notation, we're typically writing the performance of the NOT gate. We'll say Z equals A bar, or it's also written as A prime. Now, it's important to appreciate that the symbol we're drawing here with an input of A and an output of Z is an abstraction. If I wanted to build that circuit in the real world, I would go and buy something like an IC 7404, let's say. Now, this would come, a small package, and I'd actually have some tangible hardware where I could put that together. And if you were to explore the schematic of this piece, you'd see multiple NOT gates on a single IC here. Okay, so for example, this 7404, the schematic has 6 different circuits. and I would apply my VCC at top. I connect the ground pin to ground, and I'd have 6 different NOT gates to work with here. So for example, if I gave an input into 2A, I get an output here in 2Y of Z, right? So this particular manufacturer is calling A the input and Y the output. And I could build this circuit on my own if I wanted to, sort of something similar to what you may have encountered in 350, let's say, by grabbing a transistor from my part kit, attaching this to a power supply, and I could actually build my own logic gate if I wanted to here. So here's a quick schematic where you have VCC at top, you have maybe a 100 ohm resistor, let's say, you've got your NPN transistor, and by feeding a high or low signal in at A, you could monitor the output at Z to give you the inverted signal there. Now you'll see in more complex schematics, such as the 7404, here is the schematic that you'll see if you open up the user manual. Obviously more complex, but if you boil it all down, you can convince yourself that in fact it is quite a simple circuit built with nothing more than transistors and resistors here. So let's explore that idea that we could actually build our own real-world logic gate by simulating, in this case, the construction in Circuit Lab. So here I have a relatively simple circuit. I have a 5-volt VCC connected to a 100 ohm resistor, connected to an NPN transistor. I'm using a voltmeter to read the voltage across the transistor from collector to ground. And then I have a second power supply of 5 volts here with a switch that I'm going to use to modulate the input to my transistor low to high. So when the input to my transistor is low, in this case when the switch is open, right, there's no current flowing through my transistor. So my collector should be at VCC, or in this case 5 volts. So let's go ahead and simulate that. And sure enough, we see 5 volts across our voltmeter here, right? So our input is low, our output is high. Now let's go ahead and close the switch. Okay, now the switch is closed, so the input to our transistor is high, the transistor is effectively turned on, you could think about it, and current is flowing, right? So all the voltage drop will be across my resistor, and now my voltmeter should be reading 0 volts, right? And we see here, we've dropped down to 0 volts, right? So the input to my NOT gate, the output will be inverted from that input state. Let's take a look here at the AND gate. The AND gate is drawn, as you see here, sort of a truncated oval. And I have inputs now A and B, and I'll be looking at the output of Z. So if I construct the truth table for my AND gate, you'll notice it's again an exhaustive listing of all the inputs and outputs. And only when both of the inputs are high, or set to 1 here, is the output high. Now the notation for the AND gate looks like this: Z equals A times B, or A dot B. This is what's known as logic multiplication. We also have the OR logic gate, which looks like the following, where I have an input A, input B, and an output Z. If you draw the truth table for the OR logic gate, what you'll notice is that only in the case, right, where the input is 0, A is 0, and B is 0, is the output going to 0, right? So the output is going to be 1 or high if at least one of the inputs is 1. Then the notation for the OR logic gate, we'll say Z equals A plus B, and this is what's known as logical addition. Here we have the XOR logic gate, where the truth table looks like the following. And what's interesting to note about the truth table for the XOR logic gate, right, is that the output, Z, is 1 or high if only one of the inputs is 1. The notation for the XOR logic gate looks similar to the OR, except now I have sort of a circle written around my plus sign, right? So this is a common notation for the XOR logic gate. Here is the NAND logic gate, or a not AND logic gate. Truth table for the NAND looking like so. And what you notice is that the output is 1 or high if at least one of the inputs is 0. Okay? So you could also draw the NAND logic gate with an AND gate followed in series by a NOT gate, right? It would have the same truth table. And then the notation for the NAND gate is going to be Z equals not A times B. And then lastly, here's the NOR logic gate. It has the following symbol, again, with our inputs A and B and the output Z. Now here's the truth table for the NOR logic gate. And as you see, the output is only high, right, is only 1 if both inputs are low, or in this case, both inputs are 0. And here is our notation then for the NOR logic gate. Here then is that summary chart again of the requisite logic gates. This is the abstractions or the representations, the symbols, if you will, for all of the gates. Traditionally, I tell students commit these to memory and also commit the truth tables for each logic gate to memory. That will really help your understanding of the material, and particularly as we continue on with the class, committing this to memory will be very advantageous.